Okay, thank you, Mr. Gonzalez. I will try to share my screen. Now you should be able to see my presentation in full screen mode, I hope.
Yes, all good.
Yeah, perfect. So welcome from my side. My name is Maximilian Schoberl. I'm very happy to be here. I'm a research assistant at the chair of materials handling, material flow logistics at the Technical University of Munich. And today I would like to present our research results on the topic of BIM integration of light construction equipment. And first of all, I would like to start off with the definition of the main two aspects in our paper. The first one is building information modeling, or in short, BIM, which is the use of a shared digital representation of a built asset to facilitate design, construction, and operation processes to form a reliable basis for decisions. So in practice, that includes object-oriented BIM models, for example, in the IFC file format, and surface-oriented digital terrain models like Land XML. That's the first part, the first aspect of our paper. And the second aspect, which we try to combine with each other, is light construction equipment. That's equipment with an operating weight of up to 1.5 metric tons. And that includes mostly handheld equipment and non-ride-on equipment like vibratory plates, for example, or chainsaws, or these kind of small equipment. And the idea was that in construction robotics and in heavier construction equipment, there is a way of integrating BIM and the equipment through data flows, through information flows, which have three main benefits. First of all, they unlock efficiency potentials in the construction process. They reduce the construction cost and increase the safety on site. And they allow the equipment sellers to develop new business models around this integration. So that was our main idea, to bring together BIM and construction equipment like it is done in construction robotics and heavy construction equipment today. So the research objective was to investigate this BIM integration with the help of a case study. And we had a four-step procedure to do that. First, we looked at the current state of the art and requirements through a literature analysis and expert interviews. And then we moved on to introduce a conceptual framework for the integration through system analysis and technology scouting. Third, we examined the requirement gaps between heavy and light equipment. And last but not least, we evaluated the framework in a construction case study. So as time is quite short, I will have a short introduction to the state of the art. The main point is that we have a three-level structure of our construction site operations. Most of the time, the highest level is project management, where we have our information model in the form of a building information model or a simulation and a site manager who's managing that. Then we have some kind of work instruction level where a foreman formulates tasks on a daily or weekly notice, and he can have help of a tool like construction site control system. And on the execution level, we have autonomous robots or automated equipment, which does the actual task execution. And the most interesting piece we found reflecting this system view is the new ISO standard under development, the ISO 15143-4 standard, which is concerned with topographical data exchange on construction sites. It also has this three-level structure, and it, as the title says, it works on, or it specifies the topographic data exchange between different machine control systems or grade control systems, however you want to call it, and with a central instance, a site management system. And so the main takeaway from the state of the art is this three-level structure, and we took that structure and did the system analysis and said, okay, in the highest level we have project management with an information model, And on the lowest level, we have the execution with the light equipment, which we would like to incorporate. So we need to build two information flows, one downwards from the information model, so as planned data to the light equipment, and then as built data from the light equipment back to the information model. And in order for that to work, we found 5 requirements, which were specified by the expert in these expert interviews. First of all, the information model needs to contain necessary information, necessary concerning the task at hand. The task has to be sufficiently specified for the light equipment so that it can do trajectory planning or whatever it takes to fulfill this task. The light equipment itself has to be able to receive, transform, and transmit data, so to operate in this information flow. And another task which we found is very critical and also difficult to achieve is the alignment of the light equipment with the information model. So that's basically positioning or orientation-wise, how does the light equipment understand the information model and the information given to it, so that it can understand the semantics and ontologies which are specified in the task. And last but not least, if we want to store these as built information back to the information model, we need a sufficient information structure, so object-oriented or point-based or something like that. With this concept, we moved into our case study. We had a case study with a vibratory plate, which you can see here. On the left side is the basic architecture, and on the right side, you can see the actual components we use. Nothing special. We used the NVIDIA Jetson. We used Wi-Fi for coupling all these sensors, and we had a U-Blox RTK boards for the RTK, so for the positioning. And with this setup, we went into our application phase where we took our concept and we mirrored it on to this compaction cycle. So the task was to compact a certain area with a certain compaction value, so a certain density. Therefore, we used an information model, in this case, a digital terrain model, and there we defined the surface area and property sets, so the compaction value. This information was specified in an XML model. IFC would have also been possible. And in the next step, we exported the as-planned data from the information model and provided the data to the construction machine in a CSV file. The construction machine used this data, so our compaction plate, and derived the required work steps, like a trajectory it wants to drive, executed the task, monitored the execution, and collected data about the construction progress and the quality. And this data was then exported also through a CSV file containing the as-built data from the construction machinery, and it was put back into the information model. In this case, in a point list, which we can see on this side. So on the left side, you can see our as planned state where we have our surface area and a compaction value in our test bed at our lab. And on the right side, you can see all the points which were saved in a list on the right. So the value on the far right is the compaction value. Then you see the positions, northing, easting, and point numbers. And so we proved through that it's feasible to integrate light construction equipment, and it's not only technically feasible, it's also economically feasible. So at this machine in the case study, we look at a value of or price of 10,000 euros. And the equipment we used to get this BIM integration was around 600 euros. So that's okay. At least the equipment manufacturer told us that it's okay. Customers are willing to pay that. We introduced the BIM integration framework, as you've seen now, and we introduced 5 requirements which have to be met in order to speak of a BIM integration of construction equipment. And for an outlook, the main points are that we need a standardized task description. so that it is clear, so that the semantics are clear to machines and also to project management level, what should be done. Also, we need to keep the interfaces between information model and light equipment transparent and simple. One way to do that is the ISO norm I told you about in the state of the art. And as the positioning system is the most expensive part of the system, it would be great to evolve into economies of scale in that part, so that more equipment will use these kind of positioning systems to be integrated into IFC or land XML files. Yeah, with that, I'm at the end of my presentation. Thank you very much for having me, and yeah, I'm open for questions now, if you have any.
Thank you very much, Maximilian. Are there any questions? You can write in the chat box of Zoom, those that are joining online, or you can ask questions live. Any questions for Maximilian? Well, I have a couple of questions for you, Maximilian. Just to clarify, what type of BIM model you were using? You were using as built or as planned design BIM models?
So we were using a land XML file, which is basically, as you can see on the right side, so we have these points, and then we have the connections of the point in another file in the XML format. And we don't have the right value, so the Verdichtungswert, so the compaction value is not in that file. We put it in the header of the file, and then that's our as planned data, and the as built data then is what you can see on the right side. So we had, for each point which was measured by the RTK, we had a compaction value written to it. The compaction value is a very heuristic data point, because it's based on IMUs and it's not that accurate. But we are working on that currently, that we get more accurate levels of compaction.
Yeah, and what do you think is or to what degree do you think you are, or what is the gap you have to bridge to get a kind of be connected or integrate a digital twin to have a cyber-physical framework here? Or updated, information to fit into your robots?
So yeah, the most difficult point we found is that you have to align the machine or the equipment with the information model and overcome this semantic struggle. So the equipment is not very intelligent or has no perception of its environment, or very low perception. So that has been the hardest part, to go through this RTK process, which is technically quite challenging, and only to save points to the information model. So if there are any other ways to simplify that, like calibrating the machine on one point and then just follow or specify the task, the path it took, and then save information along that task, that would be way easier. But yeah, we tried. So we had our ideas from the heavy equipment like excavators, which use grade control systems, and they also use this RTK system. So we try to replicate that, but maybe there are better options to align the information model and the equipment in the future.
Thank you, Maximilian. We have another question, but we are running out of time. But I would encourage everyone to ask questions offline or during the break, please, because we need to keep going, with the flow here. Thank you very much, Maximilian.
Okay, thank you.